Still seeing my screen, right? Okay. So this unit is where we're going to focus on Newton's laws, right? And what's come with Newton's laws is basically just explaining how generally, yes, it is forces, right? But like forces kind of explain how things move, not just like kinematics. We talk about just examining motion, but like how do actually we see things move? How do you generate like move into like generating like energy and all that stuff? Is like this part right here where we have forces. So it's like this middle ground too. So really coming out of last unit, the biggest thing and concept is acceleration, right? So we looked at position and how position changed over time, which got us to start talking about velocity, right? When we talk about position, we focused on displacement as much the vector quantity, because we had to start in an initial and a finish, right? Then we start getting the velocity where we have the same thing, but also we have a direction, so that we got the vector, right? And then that leads us to when we keep going down these rates of changes, right? We get to now talking about acceleration, which is the rate at which my velocity changes. And so once we stick in that acceleration range, right? Now when we start to see how an object that's accelerating, it produces this phenomenon that we call a force, right? Either which is a push or a pull. And it makes sense, right? Like I personally, right? Like I'm a semi big guy. Like I have a fist, right? If I sit here and I throw my fist at Peter, like he's gonna feel something. If I do it slow, not as much as if I do it fast. But where does that come from? Me changing my velocity of my arm with the mass that has in my arm. So where now he's gonna feel something if we make contact, right? All these words are going to be said in this entire unit, right? Now, I want to really take a lot of time going through this because it will make sense if we talk through it. So I'm glad that we have a little bit of time today, right? So that's an overview of where we're going, right? But really take from the last unit, acceleration. Like you're going to see a lot of acceleration in this unit added on top of some new stuff, right? And this is our end goal, right? You want to be able to take what we talk about now, and I'll just change the slide too. To get to this type of problem, right? Like during a football workout, two linemen are pushing the coach on the sled, right? The combined mass of the sled is 300 kilograms, and the coefficient of friction between the sled is 0.8. The sled accelerates at a rate of 0.580 meters per second, meters per second squared, and you want to determine the force applied to the sled by the lineman. It was a lot of information, right? But you're going to see that by the end of this unit, you'll be able to do problems like this just by using a couple laws, couple rules that we're going to go over right now. But I'm going to break it down to you in little bits and pieces, and let's see if it sticks. If you get confused or have any questions, please make sure that you ask me. So these are the different topics we're going to talk about, right? I'm literally going to go exceptions, balanced and unbalanced forces, net force, recognizing what type of forces we have. We're going to focus too on the difference between mass and weight. Like that's a very big thing, mass and weight. Then we're going to start going to Newton's second law of motion. But then we move into net force and that paired with acceleration. I'll spend some time on free body diagrams, go back into Newton's second law, drawing free body diagrams, speak a lot about friction, which is a very big force. Then that leads us into talking about air resistance and terminal velocity, which then brings us into the phenomena of skydiving. And then we'll do some pairing, talking about difference between the elephant and the feather. When doing kind of like a free fall motion. And then cover the one that's probably like least, I would not say remember, but like is equally important, but like doesn't get talked about as much to me in my time with physics, Newton's third law, and then go back to this Newton's second law and problem solving, right? So that's what we're going to do. Like this is a lot, but let's take our time and go through it and really try and understand what's going on. So just like how I do with our main goal, I tell you where we're going at the beginning. This is where we're going, right? Newton's laws, there's three of them. The first is that object in motion will stay in motion. Basically, an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon an unbalanced force. That might not make sense to you right now, but I'm going to break it down. But I wanted to give you where we're going. That's the first law. The second law, when forces are unbalanced, the net force is equal to the mass of the object times the acceleration of the object. That is the second law, right? We keep talking about this thing called unbalanced force. What is a force? What does unbalanced mean? We know about acceleration. What is net force? I'm going to cover all of that. Third law, for every action, there is an equal and opposite reaction. Sounds very broad, but let's break it down so we can understand this. At the end of this unit, you should understand all three laws and also understand how they are applied to solve different problems. So the first key concept that we want to talk about, right, is inertia. Inertia has a lot of different definitions, right? The first definition, right, that you could say, the tendency of an object to resist change in a state of motion, right? So inertia, how can I get something to change a state of motion? Right now, is this desk moving? No. So what if I decided to try and start pushing this desk? Pushing this desk. Is it moving?
Maybe a little bit.
Is it going towards you?
No.
No, it's not going anywhere. So we could say this has a real high urge, like resistance to change. This right here trying to push it, right? Versus me pushing this box. That goes into the next definition that you'll see. Actually, you'll see this in your packet too. I took this exactly from the practice problems. The stubborn act of the will to keep doing whatever the object is doing. This table not moving, right? So it doesn't want to stop moving. I mean, it doesn't really have a mind of its own, but it doesn't want to like move, right? So I'm trying to make it move. I have to put a lot of energy, effort to try and get it to move. That would be the stubborn act of will. So that's inertia. Once again, the tendency of an object to resist changes in its velocity. Now, when you hear that, right? The tendency of an object to resist changes in its velocity. What does that sound like?
Tendency of an object to what?
Resist changes in its velocity. Resist changes in its velocity. Exactly. What did I just say was going to be key from the last unit that will apply to this unit? Acceleration. And we see it right here. Starting off when we talk about inertia, the tendency of an object to resist changes in its velocity. The change in velocity over time is acceleration. So you can even say the tendency of an object to resist acceleration. Changing in velocity. Oh, I swear I did not plan for that. I don't know if anybody just caught that. I just said it out loud and it popped up as the next one. The tendency of an object to resist acceleration. There's four different definitions of what is it called? Inertia. Now, I think it's this last one. This right here is very important, right? The amount of inertia possessed by object, basically its resistance, is solely dependent upon its mass. Question?
No, sorry.
Okay. How you good? And you can hear me online, right?
Yeah.
All right, okay. That last one is very important. The amount of inertia possessed by object is solely dependent upon its mass. Do I have perfect? I have a problem to go right into it, right? So we have these four objects, right? A, B, C, and D, right? And we want to rank the objects from smallest and greatest inertia, right? Now, we just said it, right? I put it in the review. The amount of inertia possessed by an object is dependent solely upon its mass. So by understanding that, how would we rank these four objects from smallest to greatest inertia? Just real quick. Would be what? C, you say is the smallest because the smallest mass. Also, too, just as we're looking, right, what is mass measured in? Kilograms, right? That's the standard unit for mass, just so you know, right? That is going to come back later, right? So you see the C is 5 kilograms, right? And you're saying this is the smallest one. What would be the next one? D, which is how many kilograms? 8 kilograms. So you got C, D, then give me the last two. Okay. Is that not what we just said? The answer? Okay. And what is the explanation? Objects with the least mass have the least amount of inertia. Objects with the most mass has the greatest amount of inertia. Now, I'm glad that we talked about it and I brought it up that it's solely dependent upon its mass, but they put velocities up there. Did the velocities have anything to do talking about inertia? No, because in the review, I said it right there. The amount of inertia possessed by an object is dependent solely upon its mass. So the velocities do not matter when we're talking about inertia. So now, this is the time where I'm not looking for the right answer. I'm actually looking for your input of how you believe, right? Now, let's do this as a group online as well, too, to where we come to a consensus of saying what we believe as a class, right? So for each statement, we want to identify it as true or false. And for the review, basically, just answer based on what you believe. And so I do want a little bit of a debate. So for the first one, right? A force is required to keep an object moving in a given direction. Do we believe that's true or false? True. I have true. Anybody say false? I have a false. Now I need you to tell me why. Okay. For it to move or to keep an object moving? Okay. So you're saying true or false? So now you switch to false. Do you still say true or false? Sorry, do you say true still? You said false. Why did you say false?
According to inertia, the object, if it's moving, it'll keep moving. And
Yeah, these are on Blackboard. I'm just trying to like, so I can.
0.7.
Yeah, I was trying to do that. Hold on, real quick. Can you still see the slides? All right, yeah, that's what I want to see because I want to see the chat too. I seen somebody in the chat say false. So what are we consensusly saying? Are we saying true or are we saying false? I heard a lot of false, so I might just take false on that one. Going false? All right, so I'm gonna say the first one we're gonna say is false. Now let's go to that next one, right? An upward moving object must be experiencing, or at least usually does experience an upward force. True or false? Grace said true online. You said false. Anybody else? All right, why did you say false? Okay, you said inertia is what you need to keep an object moving. Grace, why did you say true?
I just think like if you're going in an upward motion, you have to have some type of force that's getting you there. Like if I was biking uphill, I would need to be pedaling and using like an upward force to get me there.
Okay. Anybody else have to break this tie? Because we had true and false. Whoever breaks the tie, that's where I'm going.
Does that mean it's only upward force?
An upward moving object must be experienced, or at least usually does experience an upward force. So it must be experiencing upward force if it's moving upward. Are we going with false as a class? What do you believe? Yeah, speak, yes.
Gravity's gonna be pulling you back down, no?
Is that what you believe? This is not a trick question.
Pushing you up, like some type of force.
Okay.
It depends on how long it goes out of this day. If it just continues going up for a long time, that's something. I agree with that. Where it has to have some kind of force push.
So both of you are saying there has to be some type of force pushing it up. So are you saying, so you're saying no, false, but y'all two are both saying true.
Because I feel like if there's any kind of statement that's like all or nothing, it's usually false.
Okay, so you're using like logic to get there. But y'all are saying true because if it's moving up, then it should be having some upward force. That's what y'all saying?
We're assuming that there's gravity.
Okay. So we have, so gravity being present, then there would have to be an upward force to counteract gravity. Is that what you're trying to say? Okay. But that sounds like I got 3 false and what, 2 false and 3 trues. That's what it sounds like. So I think we're going to say true for that one. So we got false, true. Now, this is basically like the same thing, right? A rightward moving object must be experienced at least or does experience a rightward force. So instead of up, it's just like going to the right. But it's the same thing. Would y'all say true or false for that? You say false. So you're going to say the same thing as your previous answer. Are you still saying true? Only thing we changed in that third one was just the direction. Instead of being up is right. So you're saying false, which is different from what you said before. Why'd you switch your answer to false for this one? So you're basing your answer based off of gravity. And so now because there's no gravity left or right, you're saying that it wouldn't hold to where you're saying false. Okay. So we got 1 true. Go ahead.
If I'm pushing this paper to the right, then there's no force that's right.
Okay. Okay. That's what you believe, right? Okay. So you still say true. You say false. Anybody, you said false too, right? Anybody on chat say false? Or true? If you did, I could see it if you pop it up. But right now, what is that? Is false winning for that one? So we got, what did we come up with? First one we said was false. Second one true. Third one false. And then now let's go to the fourth one. A ball is moving upwards and rightward towards its peak, right? The ball experiences a force that is directed upwards and rightward. This is pretty much assuming the same thing. It's moving up and to the right, so it must experience a force that's going up and to the right. True, false. So we got false, true. Who breaks the tie? So we got another false. Anybody else? What were we about to say?
I was gonna ask you to repeat the question.
A ball is moving upwards and rightwards towards its peak. So the ball must be experiencing a force that is directed upwards and rightwards.
True.
So you say true. You say true. You say false. You say false.
It must so it must be experiencing a force that is upwards towards.
Its peak is upwards and to the right, so it must be experiencing a force that's upwards and to the right.
Yeah, true.
You say true. What are you saying?
Means to the other side.
I don't know if it's towards anything. I think it just happens to go there, but there's a force that is going upwards.
But we're saying true.
I'm still sticking with true.
And you're saying
False.
false. 1, 2, 1, 2. I think you're the tiebreaker. Anybody else? On chat? Looks like we're going consensus false for that one. No, I'm just going with whoever wins the tally. So right now we got false, true. What was it? Wait, what was it? False, true, false, 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 true, false, false. All right. If a person throws a ball with his hand, then the force of the hand upon the ball is experienced by the ball for at least a little while after the ball leaves the hand. One more time. If a person throws a ball with his hand, then the force of the hand upon the ball is experienced by the ball for at least a little while after the ball leaves his hands.
Yeah.
True, true.
I feel like I'm wrong here.
Why do you say true?
Throwing the ball to someone to push it.
Okay.
And then it's gonna stay in the air until it says for a while, right?
A little while
Yeah,
after.
after you throw it, so it's
Mhm.
gonna be in the air for a while, and then gravity's gonna pull it down eventually.
Okay.
The person catches it.
The ball wouldn't be moving if there wasn't the force being acted upon.
Yeah.
And since it's going upwards, the force has a direction that it's going in. So if it's for an instant, I'm pushing that ball forward, or upwards and to the right. So if I'm putting a force on it, maybe there's no force
Pushing it.
acting on it afterwards.
So that's what it's saying. No, that's what it's saying. That's what it's saying. It's
What's
saying
the answer.
no. It's saying that. It's saying, do you believe that if a person throws a ball with his hand, then the force of the hand upon the ball is experienced by the ball for at least a little while after the ball leaves the hand? The key word is after. It's more so, is the force being felt at the time of the impact or whatever, or is it still feeling it afterwards? That's really the question. Like afterwards, like I threw the ball, I still feel the force of me throwing the ball in my hand. Let me read it again.
The ball.
The ball still feels like the force of the hand upon the ball is experienced a little bit while after. So like the ball is already going out my hand.
Yeah.
So I still feel the force. That's what it's saying. You're agreeing. Thinking. While you think, anybody have anything different? Disagree as in saying you false? Why do you say false?
And it would be moving due to inertia, and if that's the case, then it's not changing, like it's not accelerating, or anything should constant, and I don't think the force really has much to do with it, like it's for inertia.
Okay.
I think false.
So I got a false or false. True. Anybody else? False? All right, so we going false on that one. Don't sit on the fence. Pick a side. Pick a side. We almost done. A cannonball is shot from a cannon at a very high speed. The force of the explosion will be experienced by the cannonball for several seconds, or at least a little while. Once again, a cannonball is shot from a cannon at a very high speed. The force of the explosion will be experienced by the cannonball for several seconds. Why do you say false? I heard 3 falses.
The force is already acted, so now it's not the force acted that initially pushed it away.
Mhm.
Right now, there's no once that explosion is done and it's already moving, there's no real force being acted upon it except gravity, air friction, if there's anything there. Like it just has the energy to just move it. It's not the force of the cannon anymore now. It's just it has that inertia, it has that energy. But I think maybe I'm thinking about it wrong.
I don't think you should think it like that. I think that was a good way to explain what you believe. Anybody else have anything different or similar or agree? We'll see.
I say false because once the whatever it is, what is it? Is that a cannonball? Once the cannonball hits the barrel, like products of the explosion. Nothing.
Sorry, say that one more time.
Once it hits the barrel, the products of the explosion are no longer under pressure, so there's nothing to push the ball beyond its own pressure. It's not a force.
Okay.
This problem is exactly like the same as the previous one.
Which one? The ball with the hand?
It's just a higher speed, so it should be false.
Okay. So we are saying false. Not all of us, but consensus of the group is saying false. False. Let me just make sure I got the order right. False, true, false. Was 4 false? 5 was false too? Or did we say 5 was true? False? 6 was false? Okay. So the last one, right? If an object is at rest, then there are no forces acted upon that object. True or false?
True. Oh, no, false.
Why do you say false?
What does that rest mean again?
What you doing right now?
Well, gravity's acting on me right now.
So your answer is
Is false.
okay. You tell me.
It was two forces technically.
Can't be on the fence. Gotta pick a side. Pick a side. You can always go to a different side, but you gotta pick one side. It hurts to sit on the fence, to be honest, which is very pointy. I got a false. You want to join team with him, or you want to go be on your own on true?
Eric, follow me. Gravity's definitely a force, but
So you need to like open the box and know what's inside before you make a decision.
what's it? My thing is, what does it rest mean?
What you doing right now? Yeah.
Where is it? On Earth or is it in space? If it's in space, then
I think you just said you
There's still, it's like, you're gonna go down that rabbit hole, like, where in space are you? Because then you're gonna have, depending on where you are, you're gonna have gravity to catch you.
All I need to know is if I'm at rest, are there any forces acting on me? Yes or no?
Yes.
Yes, I think gravity.
So you saying because it says there's no forces, are you going to say true or false? It's saying no forces. If you agree, then if you agree, you're saying true. If you're disagreeing because it's saying no forces, then it's false. You saying true? Do you know what you're saying? If I'm sitting here right now, 'cause I think I just want to make sure that you know, if I'm sitting here right now, is there a force acting on me? Okay, so you're telling me right now that I'm sitting there, there's gravity's acting on me.
Yeah.
Which would mean that this statement is saying that I'm at rest and there's no forces acting upon me. That's what the statement is saying. I want to make sure that you see that. So then are you saying that that's true? Okay. Are we ready for the answers? So we had one true, which was 2, but everything else is false. Right?
What was one again?
Look.
How do I get there?
Oh, join the same link that's on the from last class. Yes, they're all false. It's all false. This was really to kind of please say whatever you believe. Say it out loud because we have to talk through this. These preconceptions are what not just you as a student, but most people believe when it comes to like force. And like these need to be said out loud so that we can work through them to understand what's really going on. And you need to be comfortable with, hold on. You need to be comfortable with working through yourself and talking and explaining how you feel about things, because once you start to learn like what's really going on, you want to have that practice to where you can be able to express yourself, right? Now, go ahead.
About one of those. Just
Which one?
said, like if you throw the ball to the right, the force is gonna go to the right, but you see, it goes to the opposite direction, right?
I don't want to say that it does go to the opposite direction because there are situations where what you're saying will apply, but I want to hopefully can I explain through the slides and maybe I might give you an answer to your question, because I don't want to focus on each individual situation. I just want you to see how what we believe usually is different from what we see when it comes to these laws, right? So now, right, if you looked ahead, right, we just started talking like before just about forces, right? But what is a force? A force is a push or a pull upon an object resulting from the object's interaction with another object, right? Now, when we talk about forces, force is a vector quantity, so it has a magnitude and direction. Now, logically, that's just math I'm talking about, right? But why does that make sense? Can you just push, like just push something without a direction? That doesn't even make sense, right? I'm pushing this table, but which way am I pushing it? Forward. That matters, right? Like I pushed this box. That matters where I push. See, look, that matters. I didn't mean to throw it off the table, but look, it fell. But that matters how I pushed it, because if I pushed it back, it wouldn't have fell off the table. So the direction matters. That makes sense to be a vector quantity. Now, which I just did just now accidentally, I showed you an example of what type of force? A contact force. What do you think a contact force is? You can literally use the name in the definition. What do we think a contact force is?
The force that contacts it.
Contact how? P word.
Physically interact.
Yes, physical contact. Physical contact. So contact forces are forces that happen between two objects that interact through physical contact. So me just pushing that box, that was me actually touching it, right? Why does that matter? Because not all forces are physical contact forces, but we still feel them. What is an example of a force that you think that you might not feel, that you might have physical contact, but you still feel? Exactly. Gravity. I don't have to touch you to experience gravity, right? But we experience the force due to gravity. That is called action at a distant force, right? Those are forces that happen between objects interacting without physical contact. So we got contact forces and action at a distant forces, right? The way we model these things, right, is called a free body diagram, right? So imagine you have like this thing and you have like a stick figure. You know how like stick figures, like you're playing hangman, you draw like a little center here. I have it here, and then you have like, okay, here's the head, here's this, and this, blah, blah, blah. Does it look familiar? Now take that same concept, right? Let's make us a dot, right? The center of the action interaction, right? And we use the same concept like stick figures. This is me on camera on the board, if anybody was looking. If I was to draw a stick figure, I would use right here. Now let's say I'm doing something with a force, right? So let me draw the forces. This is me getting ahead. The force is acting on this laptop right now, right? What force is always present? Force due to gravity, right? And it's always going to what direction?
Towards the center of the-
Which in this right now is down, right? So this is my force due to gravity. I'm gonna call it this F, and I'm gonna put grav underneath, right? This is my force due to gravity acting on this on my laptop, right? Now, this will get into another concept we talked about later, right? But I'm kind of going ahead. Is my laptop accelerating? Is my laptop accelerating? It's at what? Rest. So if gravity is pulling it down, for it to be at rest, which means no acceleration, something has to be counteracting it, pushing it up, right? Because how does it sit on this table? Logically, right? That something has to be pushing it up if something's pulling it down, right? It's not moving. Getting ahead, we call this the normal force. So there's a normal force that pushes up from the table that counteracts the gravity to pull it down. That's how you're able to have this laptop sitting on this table. That's how you're able to be sitting in that chair. That's how I'm able to be standing right here. Gravity is pulling me down, but there's a normal force from the ground pushing me back up. And look at how I drew these arrows. Are they around the same length or are they different?
they're the same.
Around the same length. Why does that matter? Because gravity is a certain amount of force, right? But if this force was bigger than this force, what do you think would happen?
Moving.
It would be moving. So when I draw my diagram, I need to make both of the arrows the same length because I'm showing that this is not moving, which also I'll talk to and give you a heads up. The way that we describe things that are not moving or kind of being at an equal state is called equilibrium. Have you ever heard that word? Yes. So this state right here where something's not moving, rest, or we can call it too as equilibrium, right? State of equilibrium. But that diagram right there is a free body diagram. You're going to use this entire unit to be able to describe all the acting forces on an object. Now, think about it, right? There's two forces on that object, right? But just like how we had in, well, you'll see it actually more in vector addition next chapter, right? But was my laptop moving, right? No, right? There's a force from gravity going down. I just told you there's a normal force going up, right? One has a, you could say, negative direction, right? The other one has a positive direction, right? What happens when we put them next to each other? They do what? Balance out. Now, add the mathematical quantity. What are they really doing? They're reaching zero. Reaching zero. And how we describe that is we did what? We did what? What operation did we do? We added them, right? What is the result of addition? What's the word? Sum. So we have a sum of the forces, right? The sum of the forces add up to be zero, which would also be us in our state of equilibrium. But when we do that sum of all the forces, we call that the net force. So the net force is the sum of all the vector individual forces act upon an object, right? So on this one right here, I have two forces, right? I have, let's say, I have an up force, which is my normal force, my down force, which is gravity. If I want to add them together, they both have the same magnitude but different direction, right? Let's say my normal force is positive because it's up. And then if I wanted to add together my gravity, it would have the same magnitude but a different direction. So because it has a different direction, would this be positive or negative?
Sorry, negative.
Negative. So I'm just going to put a negative in front of this, right? Now, I'm doing addition here, right? But because I'm adding a negative is also doing what?
Subtracting.
Subtracting. So now I can just do F norm minus F gravity. But look at these lines, right? Are these lines equal? So because they're equal, we can assume that the magnitude of the forces are also equal. So if this is the same as this, right? Let me just change F grav to F norm so that you can see that this is both equal to this. Anything minus itself is equal to what? Zero. Now let me just add this thing over here that looks like this. What do you think this means?
The sum of forces.
Sum of the forces, or the thing that I just called it, the
Net force.
net force. There we go. On my laptop right now, how many forces are acting on my laptop? Two. They each have a magnitude, right? One is going
Down.
and the other one's going up. Now, when I take the sum of the individual forces, I get a net force, and that net force is the sum of my up and my down, which happen to have the same magnitude but opposite directions. So now, when I add them together, they should do what? See where they should
Cancel out.
cancel each other out. So then I have a net force of zero, which we said earlier is when my in the state of what?
At rest. Rest.
Rest or E-word? Equilibrium. Did I put that there? Okay, no, I didn't put that there. But remember that, right? Lastly, this all comes with forces. I'm throwing everything with forces at you, And even if you forget it, it's going to come back to where at least you've seen it beforehand, to where it makes sense. Forces come in pairs. Remember we said earlier, equal and opposite. Equal and opposite. Do that again. Equal and opposite. You picked the cup up. The cup felt the same for equal and opposite force in the other direction. Equal and opposite. All the time. They come in pairs. Literally. Imagine you have just a little brother just typed to your head like all the time. That's how forces are. They come in pairs. You have a twin. It's just equal and opposite. Forces always come in pairs. Now, in the Newton's laws, right, it kept saying unbalanced forces, unbalanced forces, unbalanced forces, unbalanced forces. But what is a balanced force?
The laptop.
Flat top and gravity. Look something like that, right?
There should be a table.
But why are you saying the table? Why are you saying the laptop? Why are you saying even those? It's the same reason why. But why are you saying that that's a balanced force?
No motion.
So you're saying a completely equal, no motion, right? Okay. Now here's this, right? If the forces acting on the object are balanced, the object will maintain its state of motion. If the forces acting on the object are balanced, the object will maintain its state of motion. Did I just repeat that twice? I don't know why I did that. Okay. That's what balanced forces mean, right? If the forces in the object are balanced, the object will maintain a state of motion. Now, right here on my laptop, right? Is it moving?
No.
So it's not moving. That means that the forces are
Balance.
balanced because it's maintaining its what? It's the state of equilibrium, which means it's maintaining its state of
Motion.
motion. What's its motion right now? It's not moving. It's at rest. And the object in motion stays in motion. The object at
Rest stays in rest.
oh, okay. Now we see, right? Because if the forces are balanced, right? They don't just sit here, right? When will my laptop move?
What's the second?
Don't give me the physics. Say it in just regular words. When will my laptop move? When something happens to it. When I do what? When I move it. So I got to do what to it? Pick it up. I have to specifically, right? Use a P word. I have to either
Push it or pull it.
push it, pick it up, pull it, right? Which we said is a what? Force. See how it's making sense? When forces are acting on opposite or balanced, we call this state equilibrium. Make sure that you look later tonight or tomorrow on the YouTube link I sent in the thing. I'm recording all of this. Get home safely.
Thank you. Thank you, Professor.
No problem. When the forces acting on the object are balanced, we call this state equilibrium. So right now you could say this is an equilibrium. We're all at equilibrium because we're just maintaining our state of motion. Until somebody like with Peter, he just got up, right? And just walked away. Now he's changing his motion. Now all of us right now are at rest. So when forces are balanced, we also say that the net force is equal to 0. Just like we just seen in this example, right? Why was the net force equal to 0? Because the forces are balanced, which means they have the same magnitude. But what's different about them? Remember, forces are vectors. They have the same magnitude. But what's different if it's balanced? What's different? Wait, say it again. What'd you just say? I think you just said it.
Step opposite direction.
Yes, direction. Direction is what makes it to where now we have positive and negative until we add them and they cancel out. So that's why we say the net force is equal to 0. Sorry, I was like blanked out. Okay. Do we all get what a balanced force is? I shouldn't say that because that's more like asking the positive. But do we understand? Are we have a good understanding of balanced forces? So now what we do in balanced forces, what do you think an unbalanced force is?
Something that doesn't have force.
Okay, something that doesn't have an equal and opposite force opposing it, right? Now, give me an example of what you think an unbalanced force would look like. If I push the laptop, if I, like that, was that equal and opposite? I mean, was equal. Was that equal? Was that balance? No, the marker just flew over there, and then it felt gravity, and it got pulled down to the ground. Now, is it bounced? But it's not moving. But in its motion, it was in my hand at rest, and then it was flying. So now the force, as it's flying, it was unbalanced. Now, if forces acting on an object are balanced, object will maintain a state of motion. Yeah. When the forces acting on an object are unbalanced, this state causes acceleration. Causes acceleration. Acceleration is a what? Vector. Acceleration's definitional equation is the what? Change of velocity. When I just did the velocity change? Did the velocity change? Because when it starts in my hand, what is the velocity? 0. And then it goes to?
Whatever it's at when it lands.
Yes, whatever it's at. So did it change? And so we have some acceleration, right? Now let's think about it, right? How was that acceleration created? That change of velocity. How was that created for this marker? Through it. I applied some type of force. I took my hand, I angled it, cocked it back, and I threw the marker to where now it caused this object to now change its velocity and go in a different direction and at a different magnitude because it was actually moving faster. Because I applied a force to the marker. That force, was it present when it was in my hand? No, because right now in my hand, the forces are balanced. It's a normal force, you could say, from my hand. Then it's also a force that's pulling it down due to gravity. And then all of a sudden, because look, it was up and down, right? And I just have it. The forces are up and down. Gravity is gravity left to right? No, it's up and down. Same thing with normal force, right? But then I go this way and apply a force left to right that causes the marker to go which way? There we go. Because I applied an unbalanced force and left to right when there was no forces left to right, or the forces were balanced and left to right beforehand. That caused the acceleration. All right. Now we should have a good idea of balanced forces and unbalanced forces. As I grab my marker to that too. Now, with me saying that, let's look at a problem real quick. I chose this one, even though I usually don't really pay attention to this one, because it will relate to the stuff that we talked about in unit 1. What type of graphs are these? Stat graphs. Specifically, which one? Position, velocity, or acceleration? No, just look.
I don't have a computer, so.
Oh.
Let me see. I have a computer, so.
Yes, this is a velocity time graph. So now we're looking at specifically a velocity time graph. So now we're looking at the velocity time graph, and they're telling us identify if the forces are unbalanced with reasoning, right? So how will we know if the forces are unbalanced, right? Oh, let's look at the review, right? If the forces acting on an object are balanced, the object will maintain its state of motion, right? If the forces acting on an object are unbalanced, the object will accelerate. So if they're balanced, it'll maintain its state of motion. If the forces are unbalanced, it will accelerate. Now, what does maintain its state of motion sound like? Constant velocity, right? How do we know when something has constant velocity? The line is straight like this, vertical or horizontal straight line. So which description, sorry, which we have Carson buses, he's on trip, and what is he doing? His vehicle is being acted upon an unbalanced force, right? We want to see which one represents an unbalanced force. But you just said balanced forces represent constant velocity. So which graph can we eliminate? We're looking for a graph that has constant velocity. So we need to look at the graphs and see which one. Actually, let me find the sheet. What page is on? Go to, if you have the packet, balanced versus unbalanced forces, and it is problem number 5. No, balanced and unbalanced forces. Balanced versus unbalanced forces. Problem number 5. All right, so you said eliminate, we can eliminate which one? We can eliminate the first one, right? Because it's what? Horizontal, which represents 0 acceleration. And if it's 0 acceleration, that means that the forces are balanced, right? Okay, so now we need to know if the forces acting on the object are unbalanced, and the object will accelerate, right? So now, are the forces balanced in the first one? We said no, right? And no, because it's constant acceleration. Cool. Now let's go to the middle one, right? Are the forces unbalanced in the middle one? Sorry, are the forces unbalanced? We're on this inertia packet.
See the inertia. Oh,
Yeah. What I just asked? Are the forces balanced in the second one? No. Why do you say so? How do you know it has acceleration? What does a sloping line mean? What does that mean in the context of the velocity time graph? Come on. There we go. We know the forces are imbalanced because in the velocity time graph, we see that the velocity is changing over time, which means we have what word? Acceleration. And we just said if the forces acting on the object are unbalanced, the object will accelerate. So taking that reasoning, go to the next one. Are the forces unbalanced in the last one?
yes. No.
Hold on. Why you say no?
Or number 5, the last one when it's like this, right?
Not horizontal, slope, the last one.
In the middle, because it's
Third one. Third one.
This one,
Number 5, the third graph.
this one,
Yes.
because it looks like it's even on both sides.
All right. Take a step back. Describe what's happening with the velocity over time. From what you see, you're looking. This is constant. Because constant is what? Horizontal line, because what does constant mean? Constant is not continuous. Constant means that it's the same the entire time.
It's not changing over time though. It's where
Look at that one. One more time. Is it changing?
It's going up. So
Is it changing over time?
yeah, because it's going up, so that means it's increasing.
So it changes the points that's changing over time.
Yes, you're literally saying it. It's changing over time. So because that one is changing over time, what does it mean if your velocity changes over time? You have acceleration. Now, go back to what I said in the review, right? It says it. If the forces acting on the object are imbalanced, the object will accelerate. By this velocity time graph, will this object accelerate?
Is it over time?
By this velocity time graph, the third one, will this object accelerate? Yes. So because the object is accelerating, what causes the object to accelerate? Read the review, or I'll say it again. If the forces acting on the object are unbalanced, the object will accelerate. So what made the object accelerate? There we go. So now, are the forces unbalanced for the last one? There we go. And the reasoning, just go backwards. What's the reason why we know the forces are unbalanced? Yes. 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 We're getting it. See, all this relates to what we just spent an entire unit for. I had to give you an entire unit just to get you to be comfortable with acceleration because it matters for this. And that's the answers. No, yes, yes. Constant velocity, forces balance. Acceleration, unbalanced forces.
The constant velocity is full balance, right?
Yep.
I mean, velocity is unbalanced.
Not velocity is unbalanced. Other one,
Velocity changing,
which is
unbalanced. Acceleration is unbalanced.
yes. Now, why did I make you go through that, right? Because the concept of balance forces relates to the first law. Remember, we just talked about the 3 laws that I told you. I just gave them to you just raw. Just was like, here, this is what they are. Now, how did we get there? We got there from what is a balanced force? If the forces acting on an object are balanced, the object will maintain a state of motion. I put it twice. I don't know why I put it twice, but if the forces acting on an object are balanced, the object will maintain a state of motion. That's for balanced forces, right? When the forces acting on an object are balanced, we call this state equilibrium. When the forces acting on an object are balanced, we call this state equilibrium. Lastly, when the forces are balanced, we say that the net force is equal to 0. It's all the same stuff we just said about balanced forces, right? How do we take all of that and create this general law of how to describe motion, right? So for balanced forces, an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon an unbalanced force.
Which means it's opposite reaction, right?
We're almost there. We're almost there. Hold that. But an object at rest will stay at rest, and an object in motion will stay in motion unless it's acted upon by an unbalanced force. Balanced force, because why? What's pulling this marker down? What's holding this marker up? Not acceleration, another what? Force. Technically, the normal force coming from my hand because I'm holding it up. Now, if I go move it to the left or right, I had to do what? I had to apply a force to make it move. But that force in the left or right, when we holding it right here, are there any forces in the left and right right now? Now, when I do this, are there?
Yeah.
But are they balanced? No, because I'm going to my right or my left right now. This is my left. It looks right. I'm going to my left, but there's nothing in my right. So now it's moving over this way. That's what it means. And to be honest with you, balanced forces, what I just said over to the left, all these things, we just threw it all together in one sentence to create Newton's first law. An object at rest will stay at rest, which means that the net force is equal to 0 when the forces are balanced. Or the same thing, an object in motion will stay in motion. The net force is going to be equal to 0 because the object is balanced. It will maintain a state of motion. That's what we talked about too with inertia.
So all that equals inertia.
No, just no. Inertia was a concept earlier.
So
No. Don't just, yeah. An object at rest will stay at rest. An object in motion will stay in motion unless acted upon an unbalanced force. So the only thing that will break something from being in equilibrium or its net force from being a 0 or breaking its state of motion is you have to apply an unbalanced force. That's Newton's first law. Also, it's very much simply referred to as what I just put up there, the sum of the forces, sigma F, that's called sigma. That's another Greek-like symbol. Sigma F is equal to 0.
which is the E.
Yes. Which is sigma F in English, net force. So the net force is equal to 0. Now, when me saying that, right? Now, that's how balance forces lead to Newton's first law, right? So balance forces lead to Newton's first law. What type of forces lead to Newton's second law? There we go. So, because we need to know what happens when we have an unbalanced force. But we just kind of said it, right? When we have unbalanced forces, we have what? Ignore that first part. I don't know why I keep putting, I must have not deleted it. If the forces acting on objects are balanced, the object will maintain a state of motion. We know that, right? But what happens when the forces acting on objects are unbalanced? It causes what? Acceleration. When the forces are unbalanced, we cause an acceleration. When forces are, I'm actually going to change this right here in front of y'all. Can you still see the slides? Now can you? All right, hold on. What about now? It was a typo. When forces are unbalanced, we say the net force is equal to the mass of the object times its acceleration. So remember we started talking about that inertia? It's solely the part of our object's mass, right? Now, to change something's state of motion, that's inertia, the tendency to change something's state of motion, right? Like how hard is it to resist something to change, right? How hard is it for me to move? I'm a very massive person. So it takes a lot to make me change my state of motion. It takes a lot for me to get up. It takes a lot for me to sprint. It takes a lot for me to push myself or somebody to push me, right? That times whatever acceleration is the force to make it to where it's unbalanced. So you need some acceleration on top of that mass to actually change something's state of motion. That's what we say, right? And we measure that in Newton's second law by saying when forces are unbalanced, the net force is equal to the mass of the object times acceleration. Now, we just said net force, sigma F, and said, and last time what we just had, sigma F was equal to what? 0. Now, sigma F is equal to what when it's unbalanced forces? Net force, and that's equal to what when it's unbalanced forces? This is Newton's second law. Read it in English. When the forces are balanced, the net force is equal to the mass of the object times acceleration of the object. So now this sigma F is going to be equal to what? Now give me the two letters. F is the first one. Now equal sign, and then give me the two letters. You just said this mass and acceleration. What are the two letters? MA. Mass and acceleration. So if you see this right here, this is Newton's second law. The sum of the forces is equal to MA. What does M stand for? Say it louder. Mass. What does A stand for? So now we can read this in English because what does that E thing look like? And what does it say? Sigma, which means the what? S word. When you add two things, you get the. When you add two things, you get, if I add this to this marker and this marker, the what? Sum. The sum of the F was what? No, what does the F mean? The sum of the net force, well, sorry, if you say net force, you mean the sum of the forces, but read it just right now. Sigma, sum of the forces is equal to, exactly, say it one more time. The of the exactly. That is whose second law? Newton's second law. That's not mine. Newton's second law. Now, breaking it down, right? Some more. Yes, this is a lot. But key concept, right? Now we understand forces. We understand forces. Now, what is understanding forces? There's different types of forces. Remember how I said it's two types? I'm just generalizing and putting in two types, right? You got forces like, remember when I pushed this off accidentally? What type of force was that? Push, right? I had to do what to it? I had to push it, which means I'm doing what? I'm applying pressure, which means I have to do what to it? Touch it. Touch it how? P word. Physically touch it. So I have to make physical contact. That's a contact force. When I actually make physical contact, right? What type of force is that? Frictional force. Something sliding across the table. That's physical contact. That's like when two things are rubbing against each other, it creates friction. That's a frictional force. That's a contact force. Tension force. This clock most likely has a string on behind it that's on top of a nail. That string holding this clock up, that's a frictional force. Or if you were to hang the chart, it didn't hold, but yes, me holding my phone from the cord, that's a tension force. Tension, because it's on a string, wire, cable, string, wire, cable. Anything else? Rope, yes.
So the tension force is a string force.
String, wire, cable. Yep, string, wire, cable. Normal force. The force applied from some type of push or upwards, like if you're holding something on a table, right? So I'm getting pulled down from gravity. Your bag is getting pulled down from gravity, right? But what keeps your bag on this table? An equal and opposite force that pushes against from a surface. That is a normal force. Normal force, but it has to push up from what? A surface. Contact.
So it's what?
Pushing up from a surface.
Against gravity.
Yes, so just say it's not always, yes. Just say it's perpendicular to the surface. So most likely it will be against gravity. So perpendicular to the surface. But this is all in the slides. All right. Another one, air resistance force, right? Who's rode a motorcycle? He don't gotta be a motorcycle. Been on a bike before. In the summertime, right? You're going as fast as possible. What do you start to feel? The wind, right? And usually is the wind going in the same direction as you? I mean, I don't want to assume, but is the wind usually going in the same direction to you? So you're going one way and you feel it coming towards you, right? So you're going against the wind, right? That's like friction, but with the air. That's what we call air resistance. They'll literally compare it to that as well. Imagine friction, but just with air. That's air resistance force. Riding a bike is the best example. You're riding really fast, you will feel the air.
What is air?
Air resistance, like frictional, but just air. So like,
Friction up, you sound like an airplane?
yes, literally that. Yes. All right. Remember, I had my marker, then I threw it across the room. I had to do what? I had to apply a force to make it go. Applied force, a push, a pull, a kick, a punch, something to where you have to apply the force. You have to actually go ahead and do something and put that force there. That's what applied force is. It's very general because it could be any type of force. Like it could be you throwing something, could be you catching something, it could be you moving, pushing, or pulling. That's why we have applied force for those general actions. These are your basic types of contact forces, right? But these are ones that you have to physically touch. What are some forces that you would think that you would experience, but you don't physically touch? I missed one. Who has a mechanical pencil? How does the lead come out your mechanical pencil? You push it down. What makes it come out?
Push against it.
The push against it, right? It just magically, it just comes out. Exactly. There's a springing side, right? So we have spring force. I squeeze this mechanical contraption, right? And it comes and it expands and it pushes something out and moves something physically, just like you just did with your pencil. Yes. That is a spring force. Pen, same thing. Spring force. You can measure the constant and then how far you push the spring, and it'll tell you how much force to give. That's exactly how it knows how much to put lead out. But we just said it. The forces that don't require physical touch contact but are still present, gravitational force. You don't have to touch to do anything to feel gravity, but gravity is happening right to you right now. Now, why do we focus so much on gravity in this class? Because gravity is one of the first action at a distance forces that actually is similar and can help you conceptualize forces that you cannot see, but you know are present. Like what? Electrical force. Without any real high-tech equipment, can you see an electron right now?
Thermal force.
Can you see, unless it's very hot, but can you see that? Can you see it right now? But you experience it. You experience if it's hot out. You experience if you see you're charging your phone right now. There's electricity. You can see that. We know that it's working. But can you literally see the electrons moving right now? No. And you can't touch them, but that force is still there. Same thing for magnetic force. What is it, the one? You put your cell phone next to your key card when you go to a hotel. Will it work? You might not be able to touch that magnetic force, but it's very much there. That's why they say don't put your cell phone next to your key card because it will literally erase it. Yes, that's magnetic force. So gravity gets us into that direction of understanding forces that we cannot physically touch, but they're still there and have to be measured. Now, this is for anybody who is trying to memorize anything that I was just saying about the different types of forces. No, I already got it here for you. Follow along with me, right? Weight, or the force due to gravity, that is a type of force, right? That force is the force at which the earth, the moon, or other massively large objects attract another massively large object towards itself. Very simple. Weight. Weight. The force due to gravity is also called weight.
So the force of gravity is called weight.
The force of gravity is also called weight. Weight. Because what do we know? Do you weigh the same thing on Earth as you weigh the same on the moon? No, because what's different? The gravity, which is a gravity by itself is a what? Gravity by itself is a acceleration, but the force due to gravity, which is your weight, depends on the what?
Mass.
Times the acceleration. Newton's second law. The normal force is the force exerted by a surface as an object moves across it. The normal force is what keeps this balanced to where this doesn't go through the table. Obviously, it's not going to go through the table because it's a lot more material right here. Like we talk about matter and stuff, right? But like the normal force pushes up against gravity on this marker as it slides across. Or if I hold it right here, normal force pushes against a surface. Mechanical pencil, spring force. The force exerted by a spring upon the objects connected to it at its two ends, right? Squeeze, 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 you let go, it expands. You either get let out your mechanical pencil or something with your brakes. Like literally, it's all the same stuff. Frictional force. It's the force exerted by a surface as the object moves. As I shift this ruler back and forth, back and forth, back and forth, you can literally hear it right here. That friction between this wood and this desk, that is frictional force. Air resistance. Imagine the same thing, but just in the air. You fly in a plane, you feel the air coming back. Well, you don't feel it, but the plane is going to feel the air. You're riding a bike, you will feel the air. Air resistance. Tension, string, wire, rope, or cable. That's what pulls things together. String, wire, rope, pull, or cable. When we're dealing with tension, most likely you'll be looking at situations. I think one of the final exam questions I use is an equilibrium case. So equilibrium case. Give me an example of an equilibrium case where you use a string. There's one right in your face right now. Yes, I just said it earlier.
Oh, the phone. And the charger, the phone charger.
Phone charger, yes, but also another one that we use all the time that we just don't really think about that I just said earlier. The clock is being held by what in the background?
Nail. And
A nail and a hook or a string. The string on the back of that clock, and it's a nail right there, and you just hang it right there. That's one of your problems for your final exam. Because when you have a frame, you have a picture, right? You want to hang it on your wall, you put a nail in and you put it on top of we put the string on top of it, and it just hangs there. How do you calculate how much force you need to be able to hold it, right? Or really, what does that turn into? Where do I need to put this? I can't even say it. Where do I need to put this frame at? Angle it to where it's not too much on one side versus the other side, because it'll start to lean. Or say your string is not strong enough, over time, break, because it's been feeling this force for over time and it cannot hold that. if you put at a certain angle. So you got to find the right angle to hide it to where now your sign is nice, perfect, looks nice, but also can last long and stay up there. Yes, this is literally that. Yes, exactly. Last one, applied force. Push, pull, person, object. Applied. In this section, you will see all of these forces, right? Now, talking a lot. Now let's do a problem. Oh, wait, no, we're not there yet. Hold on. So now, that's the English behind it, right? What's the symbol for a weight or force of gravity? That right there, F grav. And there's an equation for it too. Remember I said this last class, the force due to gravity or your weight is mass times your acceleration due to gravity, M times G. What did we say G was? Gravity is what? 9.8, but it's also a what? What type of quantity? Acceleration. Not the force due to gravity, it's an acceleration. What does this look like? This equation. Keep it going. Mass times what? Mass times what? Mass times gravity, and gravity is a what? Which is a what? Acceleration. So what does this equation look like? Mass times, say it louder. Mass times acceleration, which is what? Look, as I'm going backwards. Look, as I'm going backwards. Mass times acceleration, which is what? The sum of the forces equal to mass times acceleration, which is what? Look on the slides. The net force is equal to mass times acceleration, which is the what? Look at the bolded words. Go over just a little bit more. Newton's second law. So from Newton's second law, we were able to calculate the force due to gravity, which is what we call mass times G. What is G? An acceleration. An acceleration. So we get this equation that where you can always figure out your weight. You can always figure out your weight, and you get that from the second law. The second law adjusted for gravity, and you can always figure out how much you weigh or wherever you're at. You can figure out how much you weigh on the moon. You can figure out how much you weigh on Jupiter. You can figure out how much you weigh on Earth by just having that gravitational acceleration, which comes from our interaction between, we'll talk more about that. But yes, now we have normal force. Normal force is represented like this. There's not any particular equation for normal force. It usually just goes, and if it's like something on a desk, it would just be equal to whatever that force due to gravity is. Force due to gravity, I'm saying force due to gravity, but if you think about it, right? Weight. If I have this water bottle, right? It has a certain amount of weight, right? It weighs something. Having this water bottle here, right? But if it doesn't move, the normal force has to be equal to what? That's the net force, but it has to be equal to gravity or the force due to gravity, which is your weight. The force that keeps this bottle up has to be equal to the weight of the bottle. Does that make sense? The force to keep this bottle up has to be equal to the weight of the bottle because the net force has to be equal to zero for it to be in a state of rest, or you were.
You can't have nothing too heavy holding something up. You can't have something on top heavier than what's on bottom.
Yes, because then it just go like crush it, right? But if it's the equal amount, then it'll just sit here, just like how your bottle is sitting right there. It's equal.
Can it be less?
If it's less, what's going to happen? It's going to be, because it's going to be
Unbalanced.
there we go. It depends. I'm gonna try it out. See if I chug this whole water.
So the net force is zero and the weight has to be equal for normal.
That's a lot of water. That was a lot. Say it one more time.
So the weight has to be equal for normal force, the weight, I just want to make sure I'm writing it down. For weight, the pushing against the perpendicular forces, the weight has to be equal. The net force is zero, but the weight has to be equal, right? For it to be balanced.
The weight has to be equal to what? For it to be balanced. What's the other force? That's the weight, but it has to be equal to what to be balanced? It's on the surface.
Has to be equal to the surface.
What force is on the surface?
So.
That one.
Because the weight is due to gravity,
Mhm.
so the normal force is the opposite of that.
So then it has to be equal to what? Gravity, right?
Yes. What has to be equal to gravity though?
The weight of whatever it is.
No. You're saying weight twice. You're saying it has to be equal to gravity. The weight of the object, which is the force due to gravity, must also be equal to the normal force that is pushing up against from the surface upward. The normal force. There's two forces. Exactly what's on the board right there. You have a normal force. When my laptop sits right here, there's a normal force that pushes up. That's also equal to the weight. Sorry, the force due to gravity, which is the weight. In English, what am I really saying? How much this object weighs, the laptop weighs, is equal to it being pushed up, the amount of force being pushed up off the ground to help it hold it. So like, this is just being held up, like with the same amount of force as it's being pulled down because of the weight.
So the empty bottle of water, is it because it has less mass that it would potentially fall? Or
What would potentially make it fall right now? Because technically this table is supporting it with enough normal force for its mass, right? For its weight, right? What would make this fall over?
But it's more likely to fall than a full bottle because
Why?
it has lower mass.
What would cause it? Now, why would you say that? Why would you say that? Because what would make it
Because
fall
there's
over?
less stuff in it.
And what would the stuff do?
Increase the amount of force needed.
Hold on, to increase the amount of force. What makes it harder to move over?
Weight.
Is it the weight? The mass? Because of the, what was the first thing we talked about today?
Inertia.
Because technically, what's its state of motion right now?
At rest.
It's at rest, right? Inertia is the tendency for object to change its state of motion, right? So an object has a higher resistance to changing its state of motion when it has more mass. So if this has water in it, it'll have more inertia, which also has, because it has more mass, which means that it's easier for me to just flick this over when it has no water in it versus if I have a full bottle, I have to put a little bit more force to it. But that makes sense because water in it has more mass. Without the water, it has less mass. Are we following?
Object has highest resistance to change. Because it's motion depends on mass, right?
Not motion. It's the fact that it has more mass. Now think about it. If you were to try and push me over and then push over that desk, which one would be easier to push over? The desk, because the desk is less massive than me. I mean, I would assume so. Like, doesn't look like it would be hard to move that desk. It might take a little bit more energy to move me, but it's that. But it's because of the mass. Because we're both, me and the desk right now, are at a state of rest. So changing us and making us accelerate takes a lot different amount of force. Spring. That K is a constant. By the material of the spring, that's what tells you how strong a spring is to be able to make it move. And that X is a distance. What distance you think that relates to? Or a position. You could say change of position, right? That X relates to position. Huh? I don't need a unit, but just what do you think that relates to within a spring, right?
Or you stretch it.
Yes, or you compress it and then it goes, right? Like if I go like squeeze it, like if I squeeze all the way through, right? When I let it go, it's gonna have more or less force. Yeah, because if I'm like squeezing it like real close, by the time I let go of it, it's gonna just go boom. That's like if you just pressing your mechanical pencil, like it's gonna just continue to come out, right?
So the K is constant.
Like it's a spring constant because springs can be made out of different materials, right? So that specific spring, and also because of like how it's coiled and stuff like that, like it's gonna be specifically have a certain rate proportional to how much you stretch it. So like if you push it in this much, it'll get this force out. It's about the material. It's like the material, like whatever you use, like if you use like copper, steel, along with the coils. So you know how a spring is like coiled, like around, depending on how you use the coils and how you like make them, how tight they are, then that will give you the force. But that's like literally a number that you calculate and you have it ready to go. And you just, how hard I push it, then you figure out the force. But just know there's an equation for it. So anytime you see a problem and it talks about spring, they have to give you, or they give you either force, they give you one of these three. They give you the force, the spring constant, or the position. Friction. We can measure friction, right? Friction is equal to mu times the normal force. What is mu? Mu is that upside down U, which is the coefficient of friction, right? So each type of object, right? Each type of surface has a coefficient of friction. It's a number between 0 and 1.
You said each type of surface has a coefficient,
Yes, it has a number, between 0 and 1. That shows how
0 or 1, right?
between 0 and 1.
0 or 1.
Yes, it's a number between, it'll be a number between 0 and 1. It will never be bigger than 1, never be less than 0.
What's the difference between a coefficient and a constant?
It's just the number that goes in front. Like coefficient, say it's tied to like a, you would say it's like more tied to like a variable, like 4x. Like the coefficient of, like say the equation is y equals 4x, the coefficient would be 4 because it's a tied to a variable versus a constant. This is for friction. For
What's the variable for?
the normal force.
Oh,
Versus if it was like a constant would just be like 4x plus 5. 5 would be the constant because it's always going to just be constant. It's never changing.
because the spring doesn't have any other like force with it, so it's a constant. Versus this one has to take into account the
You can look at both of them both as like kind of like coefficients, like because the spring constant changes by the material, same thing with there. But like when I would say constant, it would be like if you literally have something off to the side. Like say if it was like, I'm just using math. If it's 4x plus like you have y equals mx plus b, the b part would be the constant because it's over to the side. It's not attached to a variable. It's not like slope. Does that make sense? Or am I losing you?
No, that does make sense. I was just wondering why one is called a constant and one is called a coefficient.
Yeah, if you see coefficient x, like mentally just kind of put yourself to thinking like, okay, this is a number that's like a rate that's going to change with some type of variable. And right now you see the normal force, which is usually counteracting from gravity, is variable because why? Because it's about things that weigh differently. And then you have a coefficient. So like something like me, I'm going to weigh differently than someone else, but what will always be the coefficient at that time was with the surface. So it'd be like, okay, if I'm moving on hardwood versus marble, like that's a different type of friction. So like that coefficient will change. Does that make sense? Like if you slide like with your socks on like marble versus like hardwood.
And a constant doesn't, it's like
So the surface
independent.
matters.
Exactly.
So like, I know that sounds silly, but if you was on the moon and you was on that surface, it would be totally different than being on like an island just with grass, right?
That's exactly the difference. Yes. Like football players who complain about, not complain, but like when they play on turf versus if they play on grass, totally two different surfaces. So one might be faster to move on grass and one might be faster on turf. Two different surfaces. Air resistance. It's another one. It's just like counteracting. Like it's not really an equation for it, but it's just like you feel it. But air resistance is directed like that. Tension, same thing, not really an equation for it. It's just like you calculate it from another thing, usually from like weight. So like hanging signs and stuff, that is when you'll find the tension force. Applied force, same thing. A force you kind of just doesn't really have an equation. You just kind of just literally the word apply. But you will see all these forces in this type of realm. Why I did this is I repeated it to where you see the English words on the left and on the right is the equation or the symbol that go with each one. So that when we start doing free body diagrams, we don't have to write the full thing out. It's fine. We don't have to write the full thing out. And we can write the shorthand. Okay. That was a lot. Now let's do a problem. So I talk a lot about driving in this class, right? So we want to determine that each force is present or absent and provide a justification, right? So we see all the different types of forces. Hold on one second. I apologize. What was the last thing I just said? Oh, we just started the problem, right? Okay. So we're starting the problem, right? I talk a lot about driving, right? So now we have a driver, right, who has her foot on the gas pedal. The wheels are turning as the car accelerates down the road. Consider only the forces acting upon the car, right? So remember before, what are the three functions of a car that create acceleration? Brake, gas, steering wheel. There we go. So now, basically, her foot is on the gas. Is the car accelerating? I mean, honestly, it says it, but is the car accelerating? Her foot's on the gas. Yes, right? So we are on recognizing forces. We are on the eighth one. Recognizing forces, the eighth scenario. Driver, 8. The driver of a car has her foot on the gas pedal, so she's accelerating, right? Now, what force is always present? Force due to gravity. So gravity is present, right? Now, is there a spring involved in this? So is there a spring force present? Okay. Is there a string, cable, or wire present? No. So is that tension force present? Do we have a normal force present? Why do you say yes? Ground is doing what? Hold on, is pushing because is the car flying? It's on the ground. So is there a normal force present? Say it confidently. Here we go. It's touching the surface. There we go. So there's a normal force present. Now, it's accelerating down the road, right? Is there friction involved?
Yeah.
Yes. tires, all of that, right? So it's friction force present. Okay. Lastly, I will accept this either way. They didn't really kind of say it, but just think logically. Is there air resistance present? Because when you do what? When you drive, you feel the what? Wind, okay? And let's look at the explanations, right? We said gravity was present. We said no spring, no tension, but we said normal friction and air resistance, right? Like the air resistance. If an object is moving through air, then there's air resistance. Friction, as the wheels turn, they grip the road due to friction, resulting in a forward force. Normal, even when moving, the car is still being supported directly by the road surface. Yes, as it's moving across this way, it's always still being pushed up from the surface of the road. There's no springs, no spring force, no strings, no string force. Gravity is always present. So when you go through these, right, you want to do it just like this and talk yourself through it. I know gravity is always present, so it's going to be there, right? Do I see a spring? Huh?
Number 8.
Yeah, well, this is number 8, but you have to do all of these.
I didn't miss the spring tension. I guess I would put, yeah.
Is there a spring?
Hmm.
Is there a spring?
I don't know if this one is out of a car.
I mean, yes, we know this one is, but like in the general, like look at the whole car, like outside. Like, look, if you just see a car,
Ran off the spring, if it's like that.
there's springs in the car. There's
Right,
strings in the car.
Springs in the car, so I would think, yeah.
But not go that deep. Just look at the car, like right there, like surface level, like a Tesla, right? I know there's a spring inside of a Tesla, but I'm looking at the outside of the Tesla. Just what I see right now. I see car, base, I see wheels, and that's it.
So you don't go that deep, okay.
Yeah, no. Because think about it. If we go that deep, we'll be in so many different forces. And we can't do any math like that to explain anything. Now, let's revisit this, right? I actually switched this because in your book or your work, this one is directly after the forces. But I did that because mass and weight is very confusing in this class. Mass and weight is very confusing. So let's go through this. And this is, like I said before, we want to identify each one as true or false. And you need to answer based on what you believe. This exercise does not work if you don't tell me what you believe. It's not about being right or wrong. It's about you explaining what you believe, and then we go back and discuss it. So, do you believe that objects do not weigh anything when placed in a vacuum? True or false?
Objects don't weigh.
Do not weigh anything when placed in a vacuum. Vacuum, like a vacuum cleaner.
But I feel like they don't, I feel like that's mass. That would be weight.
True? False?
A vacuum cleaner?
Like a vacuum. Like basically vacuum means like, I'm just saying vacuum cleaner, but like a vacuum is like a contained area.
But it would still have gravity.
You tell me.
That might have mass. I don't know. I'm gonna go with mass.
True or false is really what we're asking. Does it not weigh anything? Does the object not weigh anything in a vacuum? If I put it in a vacuum, does it not weigh anything?
What's a space called where there's no gravity again?
Like zero gravity, like, yes. I know what you're talking about.
So it's not a vacuum.
That's like I will say that's a different concept, like a zero gravity. I would call that a zero gravity chamber. I don't want to say that that's a vacuum.
So then false.
I might be wrong. I might have to convince that. But you're saying false. Anybody else giving me an answer? It hurts to sit on the fence. It's pointy, so you have to get off and get onto a different side. False. I got 2 for false. I got 3 for false. Do objects weigh anything when placed in the vacuum? Sorry. Objects do not weigh anything when placed in the vacuum. If I put something in the vacuum, it loses all its weight, which is force due to gravity.
I say, in a sense.
In a sense, are you jumping on to true? Okay. So I got 2 trues, 3 false. Anybody else? We're going with false by majority rules. If anybody's been saying anything in the chat, I'm gonna be honest with you. I apologize because nobody's saying anything in the chat. I just checked. I was just kind of just going like I was getting in the zone. I'm not gonna lie to you. Now, today Not fun. Not gonna lie to you. I'm sitting here just talking to you. But I'm trying to get this out the way because once I get like the main stuff out the way, which is really this preconception stuff, we can start playing around with things and I can be creative. But like I have to break this part in, and this is very like conceptual. So that's why I'm like talking through it the way I'm doing. This is not really fun tonight, but it's had to be done because I'm not about to see you for like a week. So you can just sit on all of this. And this will be on YouTube, so you can watch this again. All right. Next one. All objects weigh the same amount when placed in a vacuum, regardless of their mass. False. Why do you say false?
The mass does matter, but when the mass is weight, anything mass is different from the weight.
Okay. You agree?
Yes.
You said false? Did you agree? Anybody else want to just be that person to just be like, I disagree? True? You want to argue? All objects weigh the same amount when placed in a vacuum, regardless of the mass. So if me and you were to go in a vacuum, we would weigh the same. That's what you believe? So you think if me and you go, no, I'm not, I'm repeating what you're saying. If me and you go in a vacuum, we're going to weigh the same. Okay. So I got one true. Anybody else agree?
I mean, it's the same as the previous question.
And we're all going with, all right. We got one true. An object weighs less on the moon than it does on Earth. Yes. It stopped. It's back on. Yo, that's crazy. This is just not charging this entire time. What did I just say? An object weighs less on the moon than it does on Earth. True or false? I don't even have to go back. Everyone just said true on that one. The mass of an object on the moon is the same as the mass on Earth. So we got two truths. All right. A high-speed object, say moving at 200 miles per hour, will weigh less than the same object when at rest. A high-speed object moving at 200 miles per hour will weigh less than the same object when at rest. Why do you say false?
It doesn't have an effect on.
What does that sound like? What concept that we talked about earlier?
Second law.
Second law. We can go a little bit deeper. First, the first thing we talked about today. Say it louder, confidently. Say it louder. There we go. Inertia. So take that and go to the next one, right? A high-speed moving object, say moving at 200 miles per hour, will possess measurably more mass than the same object when at rest. False. So back to back, we got false. I'm not giving answers. I'm just repeating what y'all saying. Weight is measured in pounds. Mass is measured in newtons. True or false? False. Why do you say false? Okay. To be exact, actually, no, that's fine. Because they didn't specify if they were using like a metric, because weight technically is in pounds over here in America. Okay. Free falling object still has weight. True or false? True. Anybody debate? Want to say false? Okay, going with true. Weight is the result of air pressure exerted upon an object. False. Why do you say false? Okay. You said it's due to gravity, because weight is also called a force due to gravity. How do we do? First one we said, did we say the first one was true? Or did we all say false? So we consensually said false. Did we say the second one was false? Okay. And then them two, I remember those two. The next two we said true and true. That makes sense, right? Now, false for the high speed ones. We talked a little bit about that related to inertia, right? Weight is measured in pounds, mass is measured in newtons. It really is just the other way around because think about it. What? Weight is a what? I didn't quite say it. It's a what? Force. And forces are measured in newtons. Technically, mass, which is standard, is measured in kilograms. Now, a free falling object still has weight. We said true because if I jump out of a building and fly, I'm still going to weigh the same amount as if I was standing straight up. That one's very expensive, right? Weight is the result of air pressure exerted upon us. We said no because weight is actually in its name the force due to gravity. There we go. All right. We just did all of this, right? This is what you believe. Now, after going over it, let's do this very simple exercise, right? Complete the table. Very simple. For review, the force due to gravity, which is also known as the what? What do we call the force due to gravity?
Wait,
The weight. The weight of an object is equal to its object's mass times its due to gravity. So think about it, right? If you're on Earth, how do you figure out how much you weigh? You take your
ask.
and multiply it by, which is how much? 9.81 specifically, yes, 9.81 meters per second squared, which is also what I have in this review, right? So if we want to figure out, like in this first one, how much does this melon weigh? We're going to do what? We're going to take the and do what with it? Which is, so we should get what? What?
Newton.
There we go, because weight is a what? Newtons is the unit, and units is the unit for what type of thing? Force. There we go. That's the difference between mass and weight. Weight is a force. So now think about it backwards, right? We have an apple that's approximately 1 Newton, right? How will we figure out its mass? How will we figure out the mass of an apple if we have its weight, which is a what? Start with weight. It's a what? A force, right? Gravity is pulling down on it. So therefore, is gravity at that moment balanced? Or is it unbalanced? When gravity is pulling down on you, say not on a surface, right? Let's just say move it. Is it balanced or unbalanced?
So it's.
Maha, say right. Gravity.
If there's no normal force, then it's unbalanced.
Let me make it simpler. Gravity is a what? Not the force due to gravity. Gravity is what?
Acceleration.
Acceleration. If acceleration is foreign, is there a balanced force?
No.
No. So the force is unbalanced, right? What is the equation to describe unbalanced forces? The sum of the forces, the sum of the exactly, right? And that's for any type of force. The force due to gravity, which is also your weight, is the force due to gravity is a what? A force, right? Is it a balanced force in this moment or unbalanced force? Unbalanced force. So the unbalanced force is the sum of the forces equal to the mass times the. Right now we have the force, the sum of the forces. The sum of the force on that apple is its weight right now, which is how much? How many newtons? That's not, it's approximate. So just say 1. So it's 1 Newton, right? How can we find out the mass? Why would you divide it by 9.8?
That will give us our max, so you'll have to divide both sides by 9.
And why are you saying 9.8? Because the what? There we go. The acceleration. So we had the acceleration and we had the force. We just need to find out the mass. So we just divide by the acceleration, which is what? What is 1 divided by 9.8? 1 divided by 9.8.
0.1-ish.
Something like that.
Nine point eight.
1 divided by 9.8. Say it again. About right. Yeah. All right. Do the last one. Yes. Do the last one. You have a mass. What's the approximate weight of Pat? What's Pat's approximate weight? That's his what? And you get what? Exactly. That's all this was. I'm either dividing by 9.8 or I'm multiplying by 9.8. But it's understanding the difference between mass and mass and weight. Weight is a force. Mass is not. Mass is always going to be consistent. Your weight changes because it's due to the acceleration that you feel. And acceleration is due to the gravitational pull, which differs on different places, right? I think Earth is 9.8, and then gravity on the moon is 1.67. And what does that look like visually? That looks like when you take a step, you're hopping up and moving slowly on the moon versus you moving regular here on Earth. Now, getting into more understanding. Now, we understand where that came from. Newton's second law of motion, right? An object in motion stays in motion. That's first law, actually. Object in motion stays in motion unless acted upon an unbalanced force. When the forces are unbalanced, the sum of the forces equal to the object's mass times acceleration. Mass times acceleration. So, if the forces are unbalanced, then it's equal to the sum of the net force is equal. The net force is equal to the mass times acceleration. We can use that to rank these objects in order of their acceleration from largest to smallest. Excuse me. So, looking at this diagram, right? Which object would have the greatest acceleration?
Do they all have the same mass?
So you can look at same mass or what? Same mass or
It doesn't say, but do they have the same mass?
same mass or weight. This Newton's second law of motion at the very end. I don't know what the page because my thing is different. But it's the very last one. Now, they all have the same, visibly right now, they all have the same. You just said it, whoever just said it. Weight. Because that force right there on this free body diagram at the very end is most likely weight. So they all about 50 newtons, right? Now, remember I said earlier, my laptop being on the table, it weighs a certain amount, but there's a force applied vertically from the surface, which is called the, what type of force? The normal force, right? Which is equal to my weight, which keeps my laptop on the table, not falling through. So let's look at these, right? If my laptop is on the table, right, then that means that some of my forces are balanced or unbalanced. Balanced, right? So my forces aren't balanced, which means that some of my forces is equal to 0. Now, for an object to accelerate, the forces must be unbalanced. Let's get the easy one out the way, right? We want to go from, we go largest to smallest, right? Which one you think, I wouldn't even do it that way. I'm gonna get the easy one out the way. Which one has the smallest acceleration? Why do you say B? So it's balanced, which means therefore there's what? So acceleration is equal to 0. So because all the forces are balanced in B, that one has the smallest acceleration, which would be 0. So now, from that logic, how would you tell which object has a higher acceleration based off of what? Not what number, but based off of what are you judging off to say which one has a higher acceleration?
Like the arrows, the length of it.
Yes, the arrow is the length of it, right? So which one now, with saying that, would you describe to have the next, as in the next or the highest? Is it that next? Or, okay, let me change the question. Which object would you say has the highest acceleration? Are you still saying A?
What's the one that's the most unbalanced?
Okay, the one has the
Well,
most
no, no,
unbalanced.
The last, wait,
I like the logic. The one that's the most unbalanced would be.
We'd have to add up all the forces.
is it-
Oh, wait, hold on. Say something else. You have to add all the forces, which means you have to find the sum of all the forces, or you have to find the net force. So we have to find a net force, but we have to look at it like how we did in one dimension. Look at it as up and down and then left and right, right? They're separate because they're what? Perpendicular. When forces are perpendicular, they're independent of each other. So let's look at object number A, right? Are the forces balanced in the up and down?
Yes.
Okay, so we don't want to look there, but where is their acceleration at? 20, because the forces is
less than 50
not less than 50. The forces are what?
balance?
Unbalanced, because you see a 20 newtons to your left. Do you see anything to your right? No. So what is the net force in my left and my right? That would be the direction. Yes, it's fine. But just say 0 and 20. What is 0 plus 20? 20. So technically the sum of my forces is equal to 20 newtons. So now we have to figure out, because it's 20 newtons, it has a mass. Is mass always consistent? Mass. Is your mass always consistent? Yes, your mass is consistent. The only thing that's changing is your acceleration. So now we got 20 newtons, right? For A. B, we already know the acceleration is 0 because they're balanced, right? And each one of these, like we said earlier, it must be on some type of surface, because now we see the normal force to where they're all 50 newtons, right? So we have to look to left and right. Now, you said add up the forces, right? Is there in C a force to my left? Yes. In C, is there a force to my right? Are they the same amount of size? No. So therefore, in my left and my right, do I see balanced or unbalanced forces? Unbalanced forces. Now, how can I calculate how much there's unbalanced? Say it louder. What am I subtracting?
The 10 from the 50?
10 from the 50? 10 from the 50 or 10 from the 40, because they're in the same direction, horizontal, left and right. So now take 10 from 40 and you get what? 30. So the total net force for C is what? 30 newtons. Is that more or less than A? More. Okay. So 30 is in a realm for being the largest. So we got B at the very end because B is 0. And now we got to see between A, C, and D, right? So now, what is the sum of the net? What is the net force in the left and right for object D? Left and right. 15, right? All right. Because we subtracted 15 from 3. Yeah, D. So now, with us knowing that, right? With us knowing that, right? We know that B is at the very end, right? Now, which one actually had the highest accelerate? Oh, sorry, which one had the highest force? C, right? Now think about it, right? Is the mass for each object the same?
I mean, yeah.
Technically, you can assume that because what? What's the same in each object? The 50. Which way? Down or up? It's balanced. But look, what do you think that 50 going down represents? Weights. So they all have the same weight, right? We know the acceleration is going to be constant because it's gravity. So now they have the same weight. So that means it has the same mass, right? But where do we see the imbalance at? Up and down or left to right? Left to right. So now when we rank them, right? We all know that each one of these still have the same mass, right? So when we're calculating acceleration, the mass is going to be consistent, right? But what's going to be changing?
Wait,
Not so much the weight, but left to right. What's changing? The force, right? The force. So now that we know that the mass is consistent, for the force to go up and the mass is consistent, that means what has to go up? Exactly. So if we see a higher force, we can attribute that to having a higher. So now rank the forces from highest to lowest. And we have to look at the force and not the individual force, but the what force? The net force. So whichever has the highest net force is going to be the one with the highest acceleration. So now rank them.
so the higher force equals the higher net force, which equals the highest acceleration.
Exactly. So it's what? Then next. Then next. Is that all we have for the answer? There we go. All right. I'm pushing through because I want to get as far as possible for next week. Look, we like actually are halfway there. Yo, this is crazy. Yeah, we're definitely like halfway there. So now net force and now understanding with acceleration, right? Acceleration is equal to what?
Mass.
Perfect. I'm glad you said that, right? Before we learned the kinematics, what is acceleration equal to? Say it louder. Say it louder. No, I want to hear you. You got to say it confidently. There we go. Because you said it twice. I want you to say it out loud. Because you can talk yourself through it. So now we have a similar problem that we seen earlier, right? We looked at these. What type of graphs are these? Stat graphs. You can't see it. And you still see it now. Stat graphs, right? So now we have the velocity graph, right? We look at the velocity, so we look at the one in the middle. Position on top, acceleration at the bottom, velocity right in the middle. So now with that, right? Choose the velocity time graph that best describes the motion of the cat. So Luke got a cat, drops the cat, fat cat, off a diving board. High dive into the pool, right? Upon encountering the water in the pool, the cat encounters a 50 newtons upward restraining force. So when a cat hits the water, it feels an initial 50 upward restraining force. Which one of the velocity time graphs best describes the motion of the cat? So now let's think about it, right? The cat's 5 kilograms, which is about 50 newtons, right? As soon as the cat hits the water, it feels a 50 newton restraining force. 50 newton restraining force. Because I'm going to be lazy, let me visualize. Oh, I didn't mean to do that. Okay, this is how you do it, I think. Okay, how do you go now, right? Let's make us a free body diagram, right? So like, let's say right when how do you get it to stay? There we go. What force is always active? Say it again. No, we're not gonna get that far. I'm gonna go at 8:20. Whenever we stop at 8:20, I'm done. So like 13 more minutes. But we're actually like halfway through all of this. And if your brain is fried, this is cool because I'm recording everything, so you just go through it. But what was I saying? The cat just dropped. Literally dropped. Free fall. Now the cat, once it hits a free fall, it hits the water, right? As soon as it hits the water, it feels immediately 50 newtons, right? Now, just from what they just told us, how much does the cat weigh? 50 newtons. So that's what? The force due to gravity. What direction is it? Down. Do you see me drawing? This is my F grav, right? F grav. Now with my F gravity, right? How much is that? How many newtons is my F gravity? 50, yes. Now it feels an upward force of, when it hits the water, of how much? 50, right? So now I could do an upward force. Let me just say upward, whatever. So do F upward. So, now we're doing that, right? Are the forces balanced or unbalanced when he hits the water, the cat? Balanced, right? So that means that the sum of my forces is equal to 0. 0. I got 50 on top, 50 on bottom. But when my forces are balanced, do we see acceleration? No. So on a velocity time graph, what would indicate that we don't see acceleration? A what type of line? Horizontal line. And y'all said B. Why did y'all choose B? No, I'm not saying it's wrong. I'm asking, why'd you choose B? The cat's going down, right? So think about it, right? You drop the cat, right? We talked about free fall, right? What's changing as the cat is being dropped? Speed or velocity. So the velocity is changing over time, right? And now we talked about before, right? Velocity. When you have it, you call it the time axis or you call it the axis, right? If it's positive, what does that mean? If the velocity is increasing or changing positively, what does that mean? Accelerating, but what about it? Where is it accelerating? Up, or in what direction? The positive direction, right? Now, if it's below the axis, what does that mean? In the negative direction. So going down. So now let's think about it, right? The cat's dropped out the air. So when it dropped out the air, is it accelerating? When it dropped out the air?
It's accelerating down.
Yes. Because of what? Gravity, which is the force due to gravity is your weight, but gravity itself is a acceleration. There we go. So we need to see a velocity time graph where we see some negative acceleration. So if I'm looking for negative acceleration, I need to find a graph that has a negative slope. So which graph has a negative slope in the beginning from 0 to, let's say, halfway? B, right? You could even argue no, because there's no slope, right? So now with knowing that, right? What happens when the cat hits the water? Doesn't accelerate.
It's constant.
Constant. Which line represents a constant horizontal? So we started off with a slope line in negative going down, and then we got a horizontal line that's constant, right? Now, based off of that, which one would you pick to represent what happened with the cat? B. And why?
It's not accelerating, it's constant. It's negative and then it's constant.
So negative, and remember, it has a magnitude and a direction, right? But when it's going down, is it balanced? Because think about it. Do you go slower or do you go at the same height when you're dropped due to gravity? You go faster, right? Because even like when you skydive, right? Can you just skydive and just like land?
No.
No, you have to literally
Position yourself.
position yourself because you're falling through the air. What's happening as you're falling through the air? You're getting,
Fighting against forces like gravity, wind.
yeah, but what happens if you're falling in the air? Like you jump, if I jump on a building right now, am I going to be going as slow?
Super fast.
You're going to go fast because as time goes on, you do what?
Accelerate.
Accelerating. Yes. So the description of the cat's motion while falling through the air and description of the motion after it's in the water. So how would you describe the cat's motion when it's falling through the air? Accelerating. It's literally accelerating. Now describe the cat's motion after hitting the water. Constant. Yes, there we go. That was a lot, but is that not similar to what we just said? I don't know if you can see the answer. We pick which one? They did the same thing. They said the cat will have a downward velocity, be speeding up, then have a downward acceleration. Is that not what we just seen? The cat, go ahead. The cat's motion after hitting the water. The cat will have a downward velocity with a constant value due to balance forces. Is that not what we see? Downward velocity with a constant value after it hits the water. Yes.
See?
No, no, still B.
So still be.
Yeah. Still B.
Well, yeah, that would make sense.
And all of this comes off of what? Understanding how to represent things with free body diagrams, right? So, how would I represent all the forces in this object, right? In this scenario, right? Who's ridden a sled before? Ridden a sled. Like Santa Claus.
Oh, no. I mean, I did, but I never rode it in the snow or nothing. I sat on one.
So you've been in this, okay, so you never really ran it. Okay, this might not apply to you, but
Talking about sled or sled?
okay. Sled. Like I actually, yes.
Like you're. like,
Is there
you're
something else we
going
can use?
down the hill.
Like you coming down the hill. Like if you just grab like a tub, like a big tube, and you just went down.
Oh, yeah, like one of them little, what is it, surfboard looking things in the winter or one of them.
Yes,
circle looking things you
exactly,
Come down
right.
the hill, yeah, those.
So that, right? So you reach the bottom of the hill and you've been coasting rightward while slowing down. So you're going down to the bottom of the hill, but you're coasting to the right while slowing down. How would that look by free body diagram wise? First, what forces are present?
So how would it look?
Yeah, what forces are present first?
Gravity.
Friction?
There isn't technically because you're on the surface, right? So technically there is a normal force. Now, friction. Why do you say friction?
It's like constantly like this the whole time it's going down the hill.
Sliding.
Sliding. There we go. And I will accept that. I just need to know what the coefficient is, but I don't know if they're gonna give me that, right? But so now you have gravity going down. Hold on. All right, gravity going down. Oh, it's disappearing. Gravity going down. Then you got gravity going down. Then someone said normal force, right? I'm gonna put it like kind of here. I'll talk about that later, right? So you got normal force, right? Because it's perpendicular to the surface.
I said friction because it's against air and tension. Well, no, sorry, not tension, but
Friction. So you got friction, right? Now, is friction in the direction of the motion? As in, if I'm going to the right, will friction be going to the right as well? It goes what? Which is also opposite of the motion, right? That makes sense, right? So if I'm saying it's going rightward while costing is on down, let me just say that my friction is going to the left. This is very ugly. If you could see it. That was terrible. It's just because my mouse. Now, let's see what they came up with. Okay, so they just went straight up with normal force, right? And they said coasting, no forward force. But instead of friction, they said they have what in the background? Air, which makes sense. You come down a sled.
But isn't friction gonna be a stronger force?
I would think friction would be on the bottom because like if it's on like ice or whatever, you still have some type of coefficient of friction, but that's fine. But think about it. I want you to take big picture, go back out of it. I'm coming down a hill. I should be feeling what?
Wait,
Wind. So then I'm coming down a hill very fast. I should feel a lot of wind. So they're saying air resistance. But this is what a free body diagram looks like. You look at it and you sit there and say, what forces are present? You know normal force is present because it's not off the ground. So it's still connected to the surface. Then just logically, I'm going down a hill. There's going to be air. I feel that. So that's going to be the background, right? And then there's always gravity because I always weigh something. So like then it's always going to be present. So then the gravity's going down. But now you have the three forces and it's on top of here. So now you have your three forces to represent the motion. And the next part would be to take that exactly like this sled and actually calculate it. So this is like an example of what it would look like. So we'll start from here next week. All I'm gonna say is go through literally all the ones I just did right now. There is a typo on, I think it was unbalanced forces. Yes, right here. There's a typo right here on number 10. Slide number 10, it should be unbalanced forces. Slide number 10 if you got not on the slides from Blackburn. Because I had messed it up, but it's just a typo right there. But other than that, go all the way to on your own between now and the next week. Get all the way to slide 23. We are halfway done. I can literally get this done in like 2 classes. So where we can move on and get to vectors, like start moving fast with some of this stuff. So take the next week to really just watch some of the videos. I'll upload this over the weekend, this one. And then once you get there, try some of these problems out. And once the ones that I covered, you remember you have the answers to it, but try some of the other ones that are in the same unit by yourself so you can start to learn and practice. And turn in your homeworks just ASAP. Let me stop the recording. Everyone, good night. See you next Wednesday. This Wednesday coming up.